Alright, so today let's talk specifically about the 3-watt LEDs here and, driving one of them, driving a series of them, driving, them in parallel, and then we'll also touch on the different regulators that we have. And here we have 3 different kinds that we can talk about. They all have their own pros and cons between price, flexibility, features, etc. So let's just start by talking about these 3-watt LEDs. So they're pretty cheap. They're also pretty bright. So let's run one of them. Let's run a series of them, and talk about what's going on. So the 3-watt ambers and reds both require 2 to 2.4 volts. They also run comfortably at 400 to 500 milliamps, so about half an amp. So what we're going to do here is I will put my power supply on 2.4 volts, and we will start by hooking that up to one of them. Now keep in mind, if you remember previously, we're going to want to limit or regulate the current, because we don't want these to slowly start getting hotter and hotter and burn themselves out. So I will do that as soon as I hook them up, and I'll make sure we regulate that at 400 to 500 milliamps for the one chip. So it's actually, we're regulating. I had the amperage dial turned down to a minimum, and we are regulating at 120 milliamps right now. So you're only seeing, about a fourth of the brightness of this thing right now. So I'll slowly rise it. Now we're at 230, 260, 270, 300, 350, 400. So hopefully you saw that get pretty bright. I'll drop it back down. Now here at 160, 450, 130, 500. So let's run it a little cooler, just because of the circumstances, and we don't need it to run hot. And I'm not sure what you can see on the video here, but let's run it at 350. Alright, so here it is running at 350. 2.2 volts. Now, what happens if we try to run the next LED? So we'll run 2 of them. Nothing. It doesn't even glow. Come back to the first one. It works. Again, running at 2.2 volts at 340 milliamps. So let's talk about series and parallel. When you run LEDs in series, basically the amperage stays the same. So no matter if you have one LED like we're testing here that requires 400 to 500 milliamps at 2.0 to 2.4 volts, or if you're running 4 of them or 8 of them or 10 of them, the amperage stays the same. You still want to regulate, that 400 to 500 milliamps and no more. However, in series, because of the circuitry, how it's flowing between each LED and returning at the end here, you need to add up all your voltages. So if we know we're running these chips at 2 to 2.4 volts, if we, let's say, add them all up, right? 2.4 times 4, that's 2, 2, 2, 2. And if you want to get, if you want to add them up at 2 volts or you want to add them up at 2.4 volts, it doesn't much matter. So we actually need a maximum of 8.8 volts to run all 4 of these. So let's test that theory, right? And just do enough to run 2. So let's increase the voltage from our current 2.4 volts, which is the maximum voltage you want to run one of these at. And let's double that. We'll go to, 4.8 volts. That should allow us to run 2 LEDs and no more. So I'll bring up the voltage. We're now at 4.8 volts. Let's see what happens. 4.8 volts is running 2 LEDs, still regulating at the 350 milliamps. So if we try the third one, you notice something different happens. They actually barely glow. That's because we're starting with 4.8 volts and dividing that by 3, which is giving just enough voltage for those chips to basically, just barely glow. I'm not sure if you can see that on the camera here, but it's basically like, a dot of red. Again, if we want to run the 2 LEDs at the full 350 milliamps at the appropriate voltage here, that's happening. What you don't want to do, though, is now that we're running at 4.8 volts, is run this single LED at that voltage, because it's going to spike. The current's going to spike before the regulation kicks in, and it will burn out. So let's run all 4 of them, and again, that's going to require us to need what our original number was, which was 8.8 volts, right? So let's turn this up to our 8.8 volts. Alright, and let's see what happens. There's all 4 LEDs regulated at 350 milliamps, running at a total requirement of 8.8 volts to do that. Since the amber chips require the same exact voltage and current requirements, you don't have to change anything. You do the same thing. There's amber. Okay. Alright, now that we talked about running these types of chips in series, where again the amperage stays the same for what you want to regulate one chip for, compared to 4 or 5 or 10 chips, but you need to add up the voltages of each chip. Now, another thing to keep note of that is you can actually use different required voltages in a series. So if you have a amber and a red at 2.4 volts, you could have a white here that does run at a higher voltage. However, you just got to make sure you do your math right. So let's say you have amber, red, white, white. These two require a voltage of 2 to 2.4 volts, and the 2 whites require a voltage of 3 to 3.4 volts. So you just got to make sure you add up the total voltage required between all the chips and supply that voltage. Each chip is actually sending out the request for its necessary voltage. So in other words, in series you can have mixed voltages of chips. However, in parallel that cannot be the case, and let's talk about that. So basically, when we're working in parallel, it's the opposite of series. So each chip, as you can see based on the wiring here, is getting its own power. It's not running through another. So when we apply power to this, it's actually applying the same voltage to each chip. What that means is these are white chips, so they're going to run at 3 to 3.4 volts. So if we do 3 volts, 3 volts, 3 volts, that's 9 volts. You don't want to do that. You'd only do that in series like we explained before. In parallel, you're only supplying, no matter if you have 1 chip, 5 chips, 3 chips, you're only supplying the voltage that 1 chip requires. So in this case, we don't want to add up the voltages and supply 9 volts. We only want to supply 3 to 3.4 volts. No matter if you have 1 chip that requires it, or we have 8 of them in parallel, you're only supplying the same voltage as 1 chip. So what that means is, like in series, how I said you can have mixed voltages of chips, you cannot do that in parallel, because we're only supplying a single voltage, and each chip needs to share that. The amperage, however, is you can't regulate the amperage for one chip anymore. So it's pretty much the opposite. In series, you're adding up all the voltages required and keeping the regulation of current the same. In parallel, you're keeping the voltage the same for as if you're driving only one chip, whatever that voltage requirement is. Again, for white here, it's 3 to 3.4 volts. However, you need to add up all of the amperage you want these to run at. So in other words, let's talk about this. The white chips run at 3 to 3.4 volts. So we're only going to supply from our power source a maximum of 3.4 volts. However, these are white chips that run from 600 to 700 milliamps. If we leave our regulation of amperage on 300, that's going to be, you know, quite dim, or a lot dimmer than what it can run at, because if we're only supplying 300, that means each one of these is getting a third of that, right? So that's 100 milliamps each, when each one of these can consume up to 700 milliamps. So you're running it basically at 1/7 of the brightness for each one of these chips. So let's see what that looks like. And again, we have 3.4 volts that we're starting with, and our current regulation should be on, I think it was at 350, right? So each one of these chips is only going to see a little bit more than 100 milliamps. Let's see what that looks like. So we're running this at 3.4 volts, and each chip's only getting, you know, a little over 100 milliamps, because we're only supplying the 350. So again, these can all run up to 700. So we actually, if we wanted to run this at full power, we would have to supply 700 milliamps times 3. So you're looking at, you know, for 2, that's what, 1.4 amps plus another 700, so 2.1 amps. If we do that, let's slowly supply. We're at 500, 600, 700, 1 amp, 1.5 amps. You can see the difference in brightness. Now we're going back down. So hopefully that makes sense to a lot of people if you're watching this and trying to learn about how to drive some LEDs. We're going to get more specific into the automotive part of this and how it really applies to 12-volt charging systems and doing this inside headlights and taillights and such. But I first wanted to kind of go over, you know, understanding. You need to understand how to drive chips individually as well as in series to create, you know, DRLs and such. Alright, now let's start talking about different types of current regulators here, LED drivers in other words. And I have 3 different kinds. So you have this, what they call an MR16. You know, you'll find them a lot in these types of LED bulbs or LED spotlights that you would attach to the side of your house and such. Basically, it's a 12-volt driver. It can take an input of 9 to 15 volts, I think, or something like that. And it can output anywhere from 3 to 12 volts or something. So, with that being said, the next one, same concept, a little bit more expensive. You can find these for about, I think, anywhere from 50 cents to $1 a piece. And these here, a little bit better made. You can see there's clearly more engineering and design going on. Same concept though. It's a 12-volt driver. This also has built-in PWM dimming, so we can go into that at some time. These are a little bit more expensive. I think you can get them around $1 to $1.25 each. And lastly, you have these, which these are actually on Amazon. I think you can get 5 of them for like $6-7. Same exact concept. They work on a much higher range of voltage, and they can output a much greater range of voltage. It's also adjustable voltage and adjustable current. So you can make this work for any array of LEDs that you're wiring. And we'll talk about that later as well. Alright, so let's specifically look at this MR16 driver, and I actually found the data sheet that I printed out so we can get specifics. So we're looking at, this is the 3-watt driver, so it's capable of basically driving 3 1-watts or 1 3-watt LED. The input voltage is 12 volts, and the output voltage is actually 3 to 11 volts, so I might have misspoke earlier. The output current is limited at 280 to 300 milliamps, with, I'm sure, a 10 to 15% variation there in terms of efficiency. However, what we're going to do is, I have my power supply at 12.1 volts. We're going to supply this chip with the 12.1 volts, and let's see what we get on the output side. So we have a meter here, and we're at 11.3 volts. So you can see there's a loss of voltage, probably to run the chip itself or whatnot. I'm not going to pretend to be an expert there, but basically I'm going to start fluctuating the voltage from my source. We're at 12.1, and you'll see how we lose voltage and the difference here. So we're at 12.1, that gives us 11.3. Go up to 12.6, 12.7, 13.1, 13.5. Let's say the charging system on the car is running at full power, at 14.5, and I've even seen it as high as 15. So we're at 15 volts here, and the output's 14 volts. So it's a volt drop at 15 volts. If we go down closer to a dead car battery, say 11.8, and we're at 11. So let's stay at 12.1, just because it's on the lower side of the 12 volt battery, but we'll start with that, and then we'll fluctuate voltages just like a car would, and we'll see what happens when we have LEDs hooked up to this. Alright, so what we have going on here is we have our 12 volt power supply source going into our LED driver. Coming out of the LED driver, we have the negative lead, which I have in my hand. We have the positive lead going into the positive of these 4 chips running in series. So with nothing attached, our 12 volts is getting outputted at almost a volt less. Now let's see what happens when we use our 12 volt input, basically the car source. I know the car is probably not going to be running at 12 volts. I'm sure it'll be at 12.6 at a minimum when it's running, all the way up to 15 as we spoke before. But starting with 12 volts, let's see what happens when we power one chip. So look at the voltage. The voltage has automatically been changed from the output of this LED driver to only be consumed at 1.8 volts for this one chip. And if you remember, this one chip runs, it's an amber chip, so it runs from 2 to 2.4 volts. So I guess we're a little bit under 2 because of the voltage drop across the wiring I have going here, and the voltmeter and stuff. Let's see what happens now if we do 2 chips in series. Now if you remember, 2 chips in series, the voltages add up. So now you can see we're reading 3.5 volts, right? We do 3 chips. Now the driver's outputting at 5.6 volts to accommodate for all 3 of these red chips. Now the 4 in series, we're up at 8.1 volts. So let's see what happens if we keep going, right? Again, this driver should be outputting at 280 milliamps, and we can check that between 280 and 300 milliamps. That's what it regulates the current at. So let's add another series of 4 here. Let's see what happens. So we can still power R1, R2, R3, R4, R5. Probably looks a little weird now because we're going red to amber, but we're at with 5 chips. Let me just make sure we don't start shorting stuff out here. At 5 chips, we're at 10.3 volts. So I believe this said it runs a maximum output of what was it, 11 volts. So if we try one more chip, what happens? You see that difference? Look how how much dimmer they are. Because we can't compensate for the extra voltage requirement from this 6th chip. Let's go back to 5. It's kind of flickering because I can't get a good connection, but and it looks like even 5 is running a little bit dimmer across all the chips. Yeah. So if it's running dimmer, let's see what's happening with the amperage between all these. So what we're going to do here is we're going to use another meter, and we're going to run all of this through the meter so we can see what's actually going on here. Alright, so again, what we have going on here is we have our 12.1 volts from the power source going into the 12 volt LED driver, and then coming out of that we have the negative lead going into the voltmeter, coming back out of the voltmeter. I will then be connecting that to the negative leads on the chips. Positive lead is supplying our output from this driver into the first chip. So let's see what happens here when we do this. So the first chip, 1.8 volts is being supplied to it, and the amperage is actually low. We only have 185 current milliamps into that first chip. 2 chips are running, still being limited at 183 milliamps, but the voltage is doubled. 3 chips, the amperage is actually rising now because we're having I guess more volts supplied to the total array of chips. Do the 4th chip. Current goes up again. We're at 260 at 8.1 volts across between the 4 chips. Again, remember, this driver should supply no more than around 300 milliamps with a 20% variable difference. 5 chips. We're at 10 volts at 210 milliamps. 6 chips, and they're very dim, and we're only supplying 150 15 milliamps. Nothing. It's dim. So 6 chips probably would not be a good limit in your application here, because if the car's battery was ever at a low 12.1 volts, this is the full brightness of 6 chips. However, we know that the car's alternator and charging system will kick in, so when it's running, we'll go from 12.1 volts up to say a good 13.5, and we know it goes higher than that, right? You know that the charging system can go up to 15 volts. So here's 13.7 volts, total of 12 volts being output from the driver and consumed by the 6 LEDs. That's 2 volts per chip, right? And they're getting 138 milliamps, which is still low for these chips. these orange, amber, and red chips can, you know, run want to run at 400 to 500. So we're still running them pretty low at 3 watts. So if we go up to say 14 volts, 14.5 volts, say the average of the charging system, we're outputting at 12.5, 12.6 volts, and each chip's consuming, you know, 200 milliamps. Now, let's say the charging system's fully kicked in, right, at 14, say 14.5 volts. When you're running 6 chips, and they're all consuming 200 milliamps, and we start, let's see what happens. Basically, we'll start again at 1 chip, running at 14 volts into this, and we'll see what the output is. It's a very low current consumption. But as you give more and more chips, it's going to slowly go up. So I would say, you know, the optimal amount of chips based on the voltage variation of a car with this driver would probably be no more than 5 chips. So you probably want to run these at 4 or 5 chips. Alright, let's talk about this next regulator here. So this is another pretty simple regulator, just like the one we just went over here, the cheaper one. If you remember, this here always had a voltage drop coming off of it. If you were 12 volts going in, you know, it would be 11.8 volts coming out. If you were 14 volts going in, you know, it would be 13 volts coming out. So there's always some sort of voltage drop. With this one here, and I don't know why this happens, if someone could explain it, that'd be great. It seems like the voltage stays perfectly the same. So we have 12.3 coming into the chip. We basically have, you know, 12.3 coming out. And as we bring this up, say 14.5, we have 14.5. So I'm not sure if this chip is just more efficient or if that changes the theory here. I mean, I know you can still, maybe you can drive more LEDs off this if that's the case, but let's continue talking about what happens here using this one. So the last driver, again, this was constant current at 300 milliamps, give or take a percentage of variable inefficiencies. This here is 350, so a little bit more. So really, all that means is you can drive chips at a higher amperage, which means theoretically your chips will just be brighter. Now, if we remember coming from the other driver, once you hit 5 chips, that was pretty much, you know, your limit. On the 6th chip, you know, you sacrificed their brightness to your LEDs. There just wasn't enough voltage to throw another one in series. So, with that being said, let's see if the voltage drop difference here does anything for us in being able to add another chip in series. So let's start again at 12 volts. We'll start with the same test. We'll see what happens. So we have 12 volts coming in from our power source. This should be always regulating the amperage or current to 350 milliamps. And because we're going 12 in, it's currently putting 12 out. So let's do 1 chip, running at 2.2. So already this, if you remember from the last chip, the cheaper chip, it was only running the LED at 1.8, and then maybe that has something to do with that inefficiency of voltage drop coming just right off the board. Now look here, this 1 chip is running at 327 milliamps. This driver limits at 350. So it definitely looks like a better driver. You know, it's running at a higher voltage per chip. It's running at a higher amperage that it's supposed to run at, be limited at. Now let's see what happens when we fluctuate the voltage from 12.1 all the way up to 14.5 or 15. So we're at 12.8, 13, 13.5, 14.5. The voltage of the chip stays the same, being consumed, and the amperage stays exactly the same. Why? Because we're constant current limiting anything hooked up out of this driver. Let's go back down to our 12.1, just to keep things consistent, like our first demonstration of this driver over here. So let's start adding chips at 12.1 volts. Now we're consuming at 4.3 volts, which is about 2.15 volts per chip. Still keeping a strong limit on the amperage for these chips at 325. 6.5 volts for 3 chips at 325. 8.7 volts for 4 chips, again still at 324. Now we're on our 5th chip, and the amperage dropped. So why are we dropping when we power 4 chips on a 12 volt source with a driver regulating all of this? We're at the full current consumption, basically say the full brightness for each chip on 4, and once we get to the 5th chip, it's still pretty bright, but look, we lost amperage between the chips. We're actually running like 80 milliamps short. Now maybe that's not physically able to be seen brightness wise. To be honest, I think I can actually see it. Maybe, hopefully you can see it on the camera. Definitely for the red. Now does the same thing happen on the 6th chip? Are we going to see the... So they are dimmer, but I don't think they're as dim as when running with that driver. Now let's go back to, how when you run 4 chips, we're basically getting the full current consumption from the driver. And you run the 5th chip, and we lose some there. So we lose some, but I think it's because our source voltage just can't accommodate the voltage requirement coming out of the chip here. Right? Because if we kick our charging system in from 12.2 volts to now say 13.3, we just gave ourselves the necessary bump in voltage to get back up to the full 323 milliamps being put out from this driver. Now maybe that's enough voltage to actually continue to put out enough for the next chip. Let's see what happens. So as you can see, they're powered much more brightly when at 13.3 volts, starting with the source to the driver and outputting out, but it's still not enough to fully power them all because we're at only 129 milliamps. So that being said, let's see what the actual spec sheet is of this driver. What can it actually fully output at? And it looks like the answer to that is it does not say. But it does tell you that it can drive up to 10 1-watt LEDs in series. And the input voltage should be 2 to 3 volts greater than the desired output voltage. So that explains why when you get to a certain amount of LEDs that either they all drop dimmer because our input voltage is not sufficient enough providing to the driver for the LEDs to consume the output voltage that it needs split up between them all. So knowing this, right, let's just focus on this driver. Knowing that, let's say a car running theoretically shouldn't be any less than 12.6 volts unless your battery was very low to begin with and it cranked over and it's starting to charge up. I probably wouldn't run any more than 5 LEDs with this driver, because again, if your car's off and you're at a show or something and you have your lights on to demonstrate, whatever sick lighting application you have going on here with your LEDs or a diffuser or whatever, you know, if your car is starting to drop at 12 volts here, you know, your brightness is going down. Your chips are running at 240 milliamps right now. If you tried to wire these chips with this driver and your battery only has, you know, 11.9 or 12 volts in it, this is what you're going to see. It's not very good. So I wouldn't even risk probably running more than, you know, 5 chips with this driver or the next one, because with the car running, you know, you're going to get that nice full, you know, 300 milliamp consumption. So if you remember the specs of the other driver, kind of told you they recommend running, you know, 3 1-watt LEDs or 1 3-watt. So I'm suggesting that you can run 4 or 5 here. Granted, we are running these underpowered, so we're not actually running them at 3 watts. That's why we can run a few more. Regardless, with these 2 drivers, you know, I personally would recommend, you know, not wiring more than, you know, 4 or 5 LEDs in series at this milliamp current volt consumption. I think I'll save the last driver here for another day. It's basically the same thing we just did. Maybe I'll get to it tomorrow. But basically, the only difference here is this actually allows you to fine-tune and limit both the voltage and the amperage coming out of this driver. So we'd always be supplying, you know, 12 to 15 volts in from the car, and we can dial this down based on the LEDs that we are driving at any array we want. So the spec sheet on these are, it can output anywhere from 1 to 36 volts at a maximum of 5 amps or 75 watts. So what's great about this one compared to these is you're kind of stuck with 4 or 5 1-watt LEDs being driven off of them. I mean, like you saw, you can add more, you can add 6 or 7, but they're really only going to glow at optimal brightness when your charging system's fully kicked in at, you know, 14.5 or 15 volts. If you shut your car off and your system drops down to, you know, 12.6 volts on the battery, they're going to instantly get dimmer. It's just not going to look good. It's not a good idea, right? With these, if I know that I want to create a DRL strip with 20 of these LEDs or 10 of these LEDs, basically anything more than 4 or 5, yeah, you can use multiple LED drivers, just have multiple pairs of 4 or 5 LEDs in series, 1 driver per each. But with something like this, we can figure out the math of what 10 LEDs are going to require, both voltage and amperage wise, specifically dial that in here, and then it doesn't matter if we're inputting 12 volts or 11 volts from the car's battery or 15 volts at its maximum charging cycle. It'll make sure that all the LEDs always get the voltage and amperage that it needs. So again, maybe I'll do that video tomorrow. So I think what I'll end this video with today will be something a little bit more interesting as we dive into more specifics of the automotive world and how to wire these up, you know, with sequencing and all that cool stuff that I'm sure you guys are more interested in. Obviously, I was totally intrigued by that stuff and still am. There's a lot of stuff I want to learn and figure out. I just, you know, the internet only shows you so much, and if I could have, you know, a freaking month with Diode Dynamics and their team of engineers and whatnot, just to learn stuff and pick their brains and understand, you know, a lot of that circuitry and the engineering that goes into it, that would just be, you know, awesome. No, I'm not asking you to do that, Paul. Just stating a fact. So let's talk about, you know, real quick here before I wrap this video up and go start editing it for you. Now that we know how the LED drivers work and how to drive LEDs, let's look at something I pulled out of a aftermarket AliExpress Chinese supplied headlight for a Ford Fusion. This was their halos that they had in there. They had 2 of them. I replaced them with the profile prism color changing ones, obviously. But this is interesting what they have here, right? You have an LED driver board, just like we kind of talked about. You have two individual LEDs here. Again, there used to be two halos. I'm only supplying one for the sake of demonstration here. So you have two, they look like Cree XML chips or something. Very high powered chips is what these are. And then you have your classic sealess rod halo diffuser. So basically how this works, right, is you have a high powered LED chip that sorry guys, I didn't notice the camera wasn't even really focused on here. So you have a high powered LED chip that basically goes on the bottom of this glass or plastic acrylic ring. And what it will do is shine the light up and help distribute it and diffuse it around the ring so it looks like kind of like a BMW halo, right? So let's see what that looks like. So what I'm doing is we're putting basically 12 volts into this LED driver. When I say 12 volts, I actually mean 13.5. Our power supply is at 13.5. Again, it's powering both of these chips, and look how bright they are. They're much brighter than even the 3-watt white that we powered in the last video at full brightness to show you what that looked like. Now when this is on this ring, you can see what happens. Right? So, let's focus and talk more about just the driver. That's kind of why I'm making this video of these chips. I only got 30% left of the camera, so I don't know if we'll be able to get to the Morimoto driver. So not sure if you heard that last comment, because the Sony A5100 sucks and it overheats if you record more than like 15 minutes at a time. If anyone knows how to fix that, please let me know. I know the older or the newer models, like the 6000 and 6100, you can, you know, power the cameras off of an external like power bank instead of the internal battery, which makes the thing overheat after 10-15 minutes. I don't think that works on the 5100. If anyone knows any other solution or I'm wrong, please let me know. But basically what I was saying was, you know, we'll take apart this XSB driver, see what it looks like, see how it performs, and we'll go over, you know, how all these chips work with this driver. So back to what we were doing here, and hopefully this doesn't overheat as fast as it just did. We were looking at this LED board and driving these chips and seeing, you know, how they work. So for this Asian AliExpress headlight halo situation. So turn them back on. Before we turn them on, actually, let's go over the circuitry here. So we have our 12 volts coming in from the power supply to this driver. Coming out of the driver, we go to this JST connector. That's then run into the chips. So first thing we have to determine, right, is how are these chips wired, in series or in parallel? So looking at the JST connector with the white wire coming out as positive and the green wire coming out as negative, if we follow the white wire around, it goes to the positive of the first chip, and then out of the negative comes this other white wire into the positive of the second chip, and then out of the negative of that comes back to the driver. So we know right there that these two chips are wired in series. So knowing that, if we power them up, we take the voltmeter, let's see what type of voltage we're getting at these chips. Six. They're so freaking bright I can't see. Give me a second. 6.4 volts, I believe. So that's 3.2 volts per chip, which, as you saw with the 3-watt power LED chips, that was the same. So these are most likely both getting driven at 3.2 volts at a very high amperage, though. It wouldn't surprise me if they're both running at 1 amp, or close to that. So let me just point these away so I can freaking see. We can actually figure out how much voltage is being supplied here. Turn these off so I can see for a second. Alright, so what I've done here is I've snipped the positive output from the board and connected the meter in between here, so we'll be able to see what consumption of amperage is running through these chips that's being supplied from this driver. Let's kick the power supply back on, and we got 736 milliamps, so almost an amp. Very bright for these chips, though. Alright, so we know how this driver is powering these chips. That, again, came out of a aftermarket 2G Fusion headlight to, again, power these halo rings through a optical engineered design. I think maybe tomorrow or on the next video, you know, we'll rip this apart and talk about this. See how Morimoto was driving their XSB LED series of halos.